here we go with our video, which is on Introduction to Vectors. So have your little vectors notes ready. So as you can guess, vectors are just sort of to do with like pictures, diagrams, where we have arrows. And those arrows have lengths, which we describe the length of the vector as being magnitude, so the length, and it also has a direction. So let's go and try some vectors. So we have scalar quantities and we have vector amounts, so vectors and scalars. Scalars are a quantity described by magnitude only. So by magnitude we mean the size of the vector or the length of the vector. So the magnitude is the same thing as the length of the vector, whereas vectors are quantities which are described by both magnitude and, what would this one be? That's right, it would be direction. So scalars are quantities described by magnitude only. Vectors are quantities described by magnitude and direction. Some examples of scalars, quantities described by magnitude only. What do you think this one would be? That's right, it would be time. What do you think this one might be? Correct, it would be length. What do you think this one would be? You're correct if you would be thinking speed. Temperature is another one. What do you think this one might be? It would be mass. And energy. So these quantities, they have magnitude, but they don't have direction. Whereas vectors, examples of vectors, which are quantities which have magnitude and direction. Some examples, similar to speed. Speed would be the scalar, so its equivalent kind of vector, though, would be, have a think? That's right, velocity. Similarly, if a scalar is length, a corresponding vector, so something which would have like the magnitude length, and it would also have a direction, would be this one, displacement. Another example would be one that we might have talked about in class already, starting with F, something to do with physics and that kind of thing. Correct, it would be force. So velocity, displacement, force. This one, momentum as well, has magnitude and direction because it's important, like in which direction are you applying the momentum. And electric and magnetic fields, for example. So just showing you that there are applications of vectors in the real world, especially if you're studying physics and engineering and that kind of thing. Okay, so next one. Vectors are often named with capital letters with arrows above them. So capital letters with arrows above the letter, or lowercase letters in bold. So some examples. Here's an example of the first one. So if we're using capital letters with arrows, that could be, for example, this, OA, meaning from point O to point A, what is the vector that's drawn? So O, remember O stands for the origin, so this little arrow is meant to be at the origin, sorry. So O would be at the origin and A would be up here somewhere. So the vector OA is this red arrow here. Notice it's got an arrow tip to point out the direction. It's going from O to A. And it's a vector because it's got this little arrow thing above it. Point O is here, it's the origin, point A would be right here. If I instead had these two the other way around and had AO, it would be going from A to O, so that arrowhead would be this way. So you could just reverse the vector by going from AO instead, or you can say negative OA. Negative OA similarly would be going in the reverse direction this way. But OA, positive OA would be going from O to A. So that's an example of representation of a vector. They could also be written in lowercase letters or in bold. So you could represent a vector with two uppercase letters and an arrow. You could also use a lowercase letter and bold writing. So this is an example, and this is also another example. So so B, they could just notice it would be in bold. If it was in a textbook or in an exam question, they would use lowercase letters and bold. So that's one way of representing a vector. That's another way of representing the vector. And the way you would label the vector is you would label the vector here. You'd put the bold B would be kind of down here, indicating that this yellow thing is a vector lowercase b. Because it is quite hard to do bold in your exams and your tests, another way you can do it is you can write C with a little line, or they tend to use a squiggle. In our textbook, they'll tend to use a little squiggle. So sometimes some students write C with a little line underneath it to mean that it means like a vector C. So this little vector here is an example of C. So you would label it kind of like C with a little line underneath it. Feel free to label them if you want. You can mark point O here, point A here. You can mark this overall vector as being B, just draw it nice and bold. And you can mark this vector as being C with a little line or a squiggle. In the textbook they put a little wavy squiggle underneath it. So similarly, notice that these have direction and magnitude. So the magnitude of this vector would be 20, so meaning that the length would be 20, the magnitude of the vector, and its direction is 35 degrees northeast. So notice, yep, 35 degrees from north going to east. It's not quite drawn to scale very much, is it? So 35 degrees, north is this way, east is that way, so northeast is kind of going that way. And notice what kind of vector would it represent in the real world, judging by those units, meters per second. That's right, this would be go back. This would be our velocity vector, meters per second, meaning it's a velocity vector. In this kind of one, would you probably think of it as being like a weight vector because it's got pounds. And it's 60 degrees southeast, so going south, east, kind of, that's why it's going down this way. This one is an example of an acceleration vector. It's because it's got the speed, change in speed with time. So acceleration, speed is a change in displacement over time, or velocity, sorry, is a change in displacement over time, and acceleration is a change in velocity over time. So miles per hour is a velocity, and if you make it per second, it's velocity per time. So 5.8 miles, 5.8 would be the length of this vector, the magnitude, and west is its direction. Similarly, the magnitude of this vector would be 120. So that would be the length of that vector there. So here they say they are represented graphically as arrows. So you've got arrows with little arrow heads on them. Notice the head points to the direction that it's going. The length of the arrow corresponds to the magnitude of the vector. So like 20 is represented by this length, 120 is that length, 5.8 is that length. Of course, they're not drawn to scale in this case. The magnitude, the direction the arrow points is the vector direction. So all these, they have magnitude, direction, magnitude, direction, magnitude, direction. Just pointing out what they are. So there are different ways of representing them. They can use capital letters, meaning from this point to that point with an arrow, or they might just use a lowercase letter, like A and B are very common, A, B, and C. A and B is the most common. A way you can also represent vector is, a common way is as a column vector. So you might have seen column vectors when you did, when you've done topics like symmetry. You're talking about translations like X units. So this many units in the X direction, translating something Y units, that many units in the Y direction, like negative, taking a shape, moving it -2 units X-wise and 4 units up-wise in terms of the Y. So we can break a vector into its X and Y components. So here's a little picture of a vector here. So here's our red vector. This one is a red vector. Its X component is the horizontal movement from that it's moving. So going from this point to this point, it's moved 3 units in the positive horizontal direction. So X would be 3, and 6 units in the positive Y direction, just because, like, you know, I labeled this picture already. Sometimes it's drawn on graph paper, so you can just count the units that it's done. So this is a column vector. For the column vector above, it's moved 3 units in the X direction, as I said, and 6 units in the Y direction. Therefore, as a column vector, it would be +3, 6, because you've got to do the X direction first and then the Y direction next. If this vector was going in the opposite direction, as a column vector, you would write it as -3, because it would have gone backwards by 3 and down by 6. So you would write -3, -6 if it was going from here to here instead. Here's another little example, which I've got here, kind of going from here to here. So imagine this way it went back 2 units, and then up this way it would have gone upwards 4 units. So that's why -2 and 4 would be that little column vector. Just pointing out that that means that it's broken into X and Y components. So two vectors, this is vector equality. Two vectors are equal if they have the same direction and magnitude. So they can't just have the same direction, they also have to have the same length. So the vectors have to be equal in length, which is the same as magnitude. So for example, these ones, would you agree these two have the same direction, but they have different lengths? That's shorter than that one. So these two are not exactly equal to each other. And similarly, this one's going in an opposite direction entirely. So as I said, two vectors are parallel if one is a scalar multiple of the others. So they're equal if they have exactly the same direction and the same magnitude, the same length. But two vectors could be parallel, like these ones, so long as they've got the same direction. It doesn't matter if they've got different lengths. So they must, to be exactly equal, they have to have the same direction and length, same direction and magnitude. To be parallel, they need the same direction, but they could have different magnitudes. So to be parallel, one must be a scalar multiple of the other. So what do I mean by that? Okay, this little lowercase vector, like thick A, bold A, -2 and 3, and let's say another vector, bold B, is -6 and 9. So these two are parallel because if you took this vector and multiplied its x and y component by the same number, you can get this one. So if you multiplied both of this one by 3, you'll get -6. And if you multiply that one by 3, you'll get 9. So the fact you multiply this entire vector by 3 to get b means that they're parallel because it's a scalar multiple. So basically, this scalar multiple is what you multiply the vector by to get b. So notice, therefore, 3a, we can say 3 is the scalar, so don't put it in bold. A is the vector, though, so put it in bold, equals big vector b, so bold b. So these two are vectors, this is the scalar multiple. Because basically times this whole thing by 3 and you'll get that. So therefore these two vectors are parallel. So let's say if A is also parallel to C, so let's say for example C could be -10 and Q. So imagine the question stated, A and C are parallel, they must be parallel. So you could work out what Q is, because going from A, here's our A, what do we multiply the x component by to get -10? We have to multiply it by 5. So therefore you can multiply its y component by 5 too, because you've already been told they're parallel. So whatever you multiply this one by to get that one, you can multiply this one by the same scalar multiple to get that one. And the scalar multiple in this case has to be 5, because -2 times 5 is -10. So 3 times 5 is Q. So Q must be equal to 15, 3 times 5. Just showing you some examples of two parallel ones. This one, these two you say they're not equal, so these two are not equal because they, although they have the same direction, they don't have the same magnitude, because this one's twice as long as that one. But you can say they're parallel because they have the same direction. This one is a scalar multiple of that one. These two, would you say that they're parallel? So the problem is that you could probably to some extent say they're parallel, because if you, or this one and this one, if you multiplied A by -3a, you would get -3a, but you're not going to be asked that at this point, so don't worry about it. Let's just move on. So some other parallel vectors. Addition and subtraction of vectors. We've got an example of a triangle A, B, C. So point A is here, point B is here, point C is there. So you're told that vector AB, remember this is another way of representing vectors where you have two capital letters, meaning point A to point B. So BA would be the vector going this way, but it says AB, so vector AB is going this way. We would say it's 7, 4, so meaning that to go from A to B, you go across by 7 and up by 4, because remember X direction and then Y direction in the component vector. This is a component vector. So for going from A to B, you go across by 7 and up by 4. Similarly, they're saying going from B to C. Going from B to C, you would go backwards by 1 and then down by 4. So backwards by 1 and then down by 4. Back by 1, down by 4. And now they want you to therefore use these two things to find AC. So AC is going from here to here. And notice to find AC, you can just add these two vectors, AB and BC, to give the resultant vector. AC is a resultant vector. If you go from here to here, it's the same as if you went from A to C. See, going from here to here, it's the same journey, it's the same overall movement as if you had gone directly from here to here. So we can say vector AC is the same thing as AB plus BC. So to always write that out as a little plan. We can say the resultant vector, AC is a resultant vector because it's a result of going from here to here. So the resultant vector, AC, is equal to AB vector plus BC. It's the same thing overall. So AB is equal to AB, vector AB, so vector AB as a component vector is 7, 4, plus BC as a component vector is -1, -4. And so notice how we can get what the resultant vector is. 7 plus -1 gives you 6. And 4 plus -4 gives you 0. And that resultant vector does make sense because the resultant vector is going from A to C. And notice that you've gone 6 units in the positive x direction and 0 units in the y direction because it hasn't moved up or down at all, has it? It's just gone 6 units to the right. That makes sense because if you went 7 units this way and then up to there, and then you have to go -1 unit this way, overall you've gone 6 units. And the 4 and the -4 have cancelled out because you went up by 4 and then you went down by 4. So that's why it's cancelled out overall. So it does make sense. So notice vector addition, you can just kind of work out, okay, AC. We haven't been told what AC is, so to work it out, we have to use the information we've been given. We've been given AB and BC. So we can add those two together to get the resultant vector, which is AC. So just add up the vectors. Remember that AC, the vector AC, is the same thing as the negative of CA. So CA, for example, would you agree CA would be -6 and 0 because you're going instead backwards 6 units. So -6, 0 would be CA, and if you take the negative of that, you'll get back to the regular one. -6, 0 would become, the negative of that would become +6, 0, and so on. So just pointing out that AC is the same as -CA. Makes sense? AC is the same as the negative of CA. Okay. So here's one you might want to try for yourself. Here we've got a quadrilateral. So we've got A, B, C, D. And we're told AB is going across 1, up 6. We're told that BC is going across 3, up 1. We're told that CD, this one, is going not across by anything, by 0, and down by 7. They want us to find DA. So DA, do they want us to find, so what you could think of, you could find AD first, and then just remember DA, similarly to the last one, AC is the same as -CA. So you could find AD first, and then DA would just be the negative of that. So let's see. So solution, DA, one way you can look at it, DA is the same as going from DC plus CB plus BA. So you could have worked out AB plus BC plus CD and then just taken the negative of that. That's one thing you could have done. Similarly, if you want to go straight to DA, you can think of it as DC. DC would be the negative of that. So notice DC we call 0, 7 instead because it's a negative of this one, DC, plus CB. So the negative of, that's a negative of BC, so make it negative, -3, -1, plus BA, DC plus CB plus BA. And BA would be the negative of AB, so -1, -6. So that's a quick way you can just get straight to it. Add these two together, add the x component, 0 plus -3 plus -1 gives -4 x movement overall. And 7 plus -1 plus -6 gives you 0 overall. Does make sense. Going from D to A, you're going backwards, so you're going backwards by 4, and you don't appear to be going upwards or downwards at all. Alternatively, as I said, you could have just gone straight to working out AD by adding these three together because they're going in this direction, and then take the negative of that answer. So alternatively, you could just have worked out AD. AD is just AB plus BC plus CD, and then add them together. That one goes there, that one goes there. 1 plus 3 plus 0 is 4. 6 plus 1 plus -7 is 0. The only thing is if you do it that way, you're just going to have to remember. Therefore, you've worked out AD, you might by accident think, hey, I've got the answer. But you would have to then on top of that at the end remember, it's not AD that we want, it's DA. That's AD, so AD is 4, 0. So DA would just be the reverse negative of that. It would be AD is the same as -DA, and so then DA equals -4. And negative of 0 is just 0. So when you're drawing these out, please don't forget to draw the little arrow. You can do an arrow with just one stroke at the top. Some people do the double-headed, double-stroked arrow kind of thing. It's up to you. I do one stroke, but it's fine, whatever you want to do. and so on. Let's do some more examples. So in the diagram, FA, EB, and DC are parallel. So these aren't talking about vectors, they're just lines. They're just saying FA, EB, and DC are parallel. And see, we've got the little arrows on there also pointing out that they're parallel. So the diagram also told us that these three lines are parallel. We've also told that vector AB is equal to ED. So vector AB is equal to ED. So they're the same vector. So hence why it can be useful to, they've been kind of also labelled A. So vector AB is equal to ED, which is the same as A. So AB, ED, they're the same vector, so we can call it bold A. Notice it's bold A. FA equals B, so where's FA? FA is this one, they've just called it B, bold B. EB, where is it? EB is equal to 3B, so that's a scalar. The 3 is a scalar, so don't do it in bold. The B is the vector, so do the B in bold, lowercase. DC is 2B. So just same as before. 2 is a scalar, so don't draw it in bold. B is the vector, so draw the B in bold. So that's just told us that information that's on the diagram anyway. Express the following vectors in terms of A, B, or A and B. So meaning like maybe it's A plus B, or maybe it's 2A minus B, or maybe it's just 3B, or maybe it's 4A. So express the following vector in terms of A, B, blah, blah. So FE, where's F and where's E? So we don't have anyone specifically for this one, but we could go down, down, down. So there's lots of different pathways. You could go all the way around. I tend to take the shortest way possible. So don't forget to write out your little plan. FE, going from F to E is the same as if you went FA, AB, BE. So write it out. FA with a little arrow plus AB plus BE. Because I chose this pathway because it's labelled. We know those ones. So we've got little labels on that one. So FA is just B. So this is bold B, so make sure you draw it in bold. AB is A, so plus A, draw it in bold. Plus BE, and BE, notice, is negative of this one. Going from E to B is 3B, so BE must be negative 3B. That's a scalar, so don't do it in bold, and this little one here you can do in bold. And then you can simplify that. Collect your like terms. B plus A minus 3B is the same thing as A minus 2B. So bold A, don't bold the 2 because it's a scalar, multiple, and bold the B because it's a vector. So A minus 2B is a resultant vector FE. Sometimes it's handy to draw these in on here. Like you might want to draw that on your diagram in case it's helpful for later. BC, da, 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 da. What's one way that we can get to BC? Let's see. We could do, so BC, where is B? What's here? BC. So BC, you could just do the reverse. You can go BE plus ED plus DC. Similarly, you could have worked out CB and then just negated it. But I'm going to go this way. I'm going to do vector BE plus ED plus DC. So write out your little plan, put your little arrows on top of the capital letters, and then pop in the little vectors. So it's going from BE, it's negative 3B, plus A, plus 2B. So negative 3B because it's going against the arrow, plus A because it's going with the arrow, and plus 2B because it's going with the arrow. So again, these are scalar multiples, the 3 and the 2. B, A, and B are vectors, so draw them in bold. It doesn't come up very bold on mine, sorry. And then collect your like terms. Negative 3B plus 2B is just minus B. So you can write it as A minus B, and these should be in bold as well. FC, where's going? FC, and So this is where maybe having written something in beforehand can be helpful. Like, you know that BC is A minus B. So that might be helpful for when doing FC. So FC, how did I choose to do it? I went a different pathway. You could have gone here, here, plus this. That would have been fine. I instead went FE, which I worked out here already. So FE plus ED plus DC, because we're going from F to C. So you could have gone this way or you could have gone this way, and you should get the same answer overall. Feel free to try both ways if you want. So FE already is A minus 2B. So A minus 2B, you don't have to have it in brackets, I just did. ED is plus A, and DC is plus 2B. Then A plus A is 2A. Negative 2B plus 2B cancels out. And again, this is a scalar, so don't draw it in bold, but this is a vector, so draw that one in little lowercase a in bold. Again, you might want to have drawn something in, like 2A, you might want to put in for FC is 2A, so don't worry about it. Well, it's a long way around. But BC might be helpful to have drawn in, and FE might be helpful to have drawn in. DA, where's DA? So DA, many ways you can go. You can go da, 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 or you can go da, 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 or you can go da, da, da. Same answer either way. So that's a way you could check it. Which way did I choose to go just for fun? I did DE plus EB plus BA. DE plus EB plus BA. I just used the ones that were originally in the diagram. So DE is negative A because it's going against the arrow. EB is plus 3B because it's going with the arrow. And BA is negative A because it's going against the arrow. And then collect your like terms. Negative A minus A is negative 2A plus 3B. So again, scalar, so don't draw that one in bold. Do the lowercase letters should be in bold, but the numbers are scalar multiples. They're not vectors, so please don't put the numbers in bold. So yeah, you can experiment with going different directions as well, and you should hopefully get the same final answer. Okay, so similarly, as I was going on about, you might have noticed adding A to B. So let's see, if you go from A to B, here is what's called the resultant vector. Feel free to draw in the right label. This one is the resultant vector. A plus B, the overall vector. This going this way is A plus B. Going in the other direction would be the negative of that. Negative brackets A plus B, close brackets, or negative A minus B. Because like going, yeah, that kind of thing. So subtracting B from A is the same as adding negative B. That might have been something you've noticed overall. So this is just a little bit of a summary of something you've probably picked up on already. Subtracting B from A is the same as adding negative B. So if you go A and go this way, negative B, it's the same as going A minus B, and so on. Negative B is the same magnitude as B, it's just the opposite direction. So negative B is going this way, positive B is going that way. So the same magnitude, same length of the vector, it's just the directions are opposites to each other. So similarly, A minus B, the resultant vector. This one here is the resultant vector of A take away B. Okay. So as I said, subtracting B is the same as adding negative B, which you've probably gotten already. Let's do another example. Try for yourself. The diagram shows a trapezium. Here's a trapezium ABC. OABC. X and Y are the midpoints. So X and Y are the midpoints of OB. So X is the midpoint of OB and Y is the midpoint of AC. Doesn't look like it because they've intentionally not drawn it to scale. The vector OA we'll label as being A. See here, OA, we've labelled it as being A. The vector OC, we've labelled it as being vector C, lowercase c, and vector from point C to B, we've labelled as being half A. So that's something that's given in the question. Find each of the following vectors in terms of A and C, simplifying your answers where possible, like collecting like terms. So OB. OB is here. OB, what's one way that you can get to OB? A pathway that's pretty easy? It's probably be to do this one and then this one. Probably the easiest path that I would suggest. Could go this way and this way, but we don't yet know this one. We know this one and this one already. So we're going to go OC and then we're going to do plus CB. So OC, don't forget your arrows, plus CB. So using this little lowercase vector notation, would be C, draw that in bold, plus half. Half is a vector, not a vector, half is the scalar multiple, so don't do it in bold. The C and the A are in bold. None of these are in bold. It's just the lowercase c and the lowercase a we draw in bold. That's the notation. Indicates that C and A are vectors. O and C are just points, like C, O and C. C and B. Once you connect them and put a little arrow on the top, it becomes a vector. But you still don't draw it in bold. So C plus a half A, you could write C plus a half A, or you can write a half A plus C, same thing overall. So that's OB. So just be aware of that. OB is this whole thing across here. So we know the whole length across here. OX. So OX, remember, they pointed out that X and Y are midpoints. So if OB is half A plus C, then OX must be half of this vector. So see, OX, it's the same as a half of OB. OX, it's the same of a half of OB, because X is a midpoint. So what I've done is I've just said a half C plus a half A, because that's what OB was, so I've just halved it. You could have written half A plus C, no problem. So a half C, half of all of this, and then I've just expanded. So a half C plus a quarter A. Half C plus a quarter A, you could write a quarter A plus a half C. Notice that they're kind of in alphabetical order, not such a big deal. A quarter A plus a half C. Overall, how about AO? Where are we? AO. Aha. Going from A to O, that's a pretty easy one. You can just look at that one. Is the answer A? No, it's not. It's going in the opposite direction. It's going against A. So it's negative A. So AO is like the negative of OA. OA is just little a. So AO must be the negative of that. So it's negative little a. Negative is not in bold, but the A is in bold. Because the negative is like the scalar quantity, -1, scalar multiple. Oops. Okay. AC. AC, how many different ways can we get to AC? You can go bam, bam, bam. Go back. But we don't know this one, so let's just do this one. Go reverse. So we're going against the A, and they were going with the C. So the little plan, I think it's really important to write out these little plans. We're going from A to O, and then we're going O to C. AO plus OC. AO is the negative of A because it's going against the arrow, and OC is plus C. So again, negative is not in bold. A and C are in bold. The plus is not in bold. So if you were to write in alphabetical order nicely like this, you would write negative A plus C. So on. Good fun stuff. So vector additions, as we said, vectors can be added graphically or analytically, kind of like we've done a lot of analytical ones, but maybe let's try a bit of graphical vector addition. So triangle head to tail method. So what you might have noticed is you draw the first vector with a proper length and direction. Then connected to the end of the first vector, you draw the second vector with a proper magnitude, like length and direction. And the second vector is drawn from the head of the first vector. So you draw your first vector, and then from the head of the first vector, you draw your second vector. The resultant vector is a vector originating from the beginning of the first vector, so from the tail, terminating at the head of the second vector. Then you would measure the length and orientation of the resultant. What vector? What on earth do we mean by that? Let's see a little example. Find the resultant of vector A, and it's A and B, different kind of notation. They've said vector A is 11 degrees north. Oops, sorry, 11 newtons, sorry, because it's a force. This is a force vector, because that's the direction here. So this vector is A is 11 newtons at 35 degrees northeast. So a length of 11. So if you want to draw it nicely, I would draw it nicely on your picture. You could use your ruler if you've got the space, 11 centimeters or whatever scale you want to use. 11 centimeters, 11 millimeters, whatever it is. Roughly, you can welcome to use a protractor if you want to do the right direction. If you want to do it vaguely, you can. Northeast is vaguely in this direction. And B is 18 newtons, because it's a force vector, in the northwest degree. So here we draw the first vector, and notice that the second vector must begin at the head, at sort of the head of the last one, and go here. And if that's 11 centimeters, then you would have to draw this one 18 centimeters. 20 degrees northwest, you can do it vaguely if you want, if you don't use your protractor for now. You can practice using your protractor another time if you like. And so the resultant vector has to begin at the end, at the tail of the first vector, and end at the head of the second last vector. So the resultant vector going from here to here, the resultant vector is going from here up to here. So if you've drawn this to scale, and if you did do it using nice angles, you could just measure the length of that one. And you would get roughly 14.8 newtons. So if this one's drawn to scale and with the right bearings, then you, using a protractor, you would have ended up with a length here of 14.8 newtons and an angle of 50 degrees northwest, 57 degrees, sorry, northwest. And I called it R for resultant vector. So just showing that you can do it analytically or draw it graphically, but drawing it graphically takes ages. An example of a parallelogram, just to finish off, tail-to-tail method. Draw both vectors with proper length and orientation originating at the same point. There we go. So this is a parallelogram method. Complete a parallelogram using the two vectors as two of the sides. So imagine the instruction to this would have been complete a parallelogram using the two vectors that were given as two of the sides. So for example, you could do another brown arrow coming off this way and another green arrow coming off this way. There you go. Kind of done. Not very exciting really. Draw the resultant vector as a diagonal originating from the tails. There's a resultant vector of drawing this parallelogram. Measure the length and angle of the resultant vector, the blue one. It's not a very good example. But we'll finish up there, and so thank you for watching.